Alright, let's go ahead and talk about dispersion. Dispersion is the idea that something changes with frequency. In terms of optics, we're going to talk about the index of refraction changing with frequency. And this is generally what most people think of immediately when they hear the word dispersion. Dispersion is really just anything with a wave that changes as the frequency of the wave changes. So you can talk about the dispersion of a beach wave coming into the shore, the dispersion of a mechanical vibration going through a steel beam. It doesn't have to be index of refraction, but in terms of optics, that's what we mean. So let's go ahead and talk about the optics part, because that's why we're here. Index of refraction changing with frequency means that if I have red light going through some medium as opposed to blue light going through the same medium, the index of refraction of these two beams, because they're different colors, different frequencies, do not see the same index of refraction. And that is basically true for every material known to man except for vacuum, because there's not really anything in it to cause dispersion. But everything else, there will be a different index of refraction for the different colors or different frequencies. And while I could spend a lot of time going through, prism angles and showing you how a pretty little rainbow is made if you shine white light through it, I'll do that really quickly just to humor you in case you haven't seen it. So one example of a prism is you have a piece of glass, a piece of normal glass. You shine white light through it, and since the red light sees a different index than the blue light, you get some kind of pretty rainbow where the different rays all experience a different index inside the glass, so they refract at slightly different angles. What I want to have you give it a better understanding, though, is why this happens, which isn't very well covered generally. I am going to go ahead and skip the idea of normal and anomalous dispersion for a bit. If you haven't heard of that, don't worry. You are about to understand far more than that, because by now I'm sure you know that I like to go off the deep end when I talk about things. I'm going to plot the index of refraction of some material. Most materials look like this, over a very large frequency range. This is a very large chunk of the electromagnetic spectrum. This is past ultraviolet, and this is very deep infrared. So in terms of optics, this is most of what we care about. Once you get further back here, most things are transparent, and this index pretty much stays flat. And past here, this pretty much stays flat as well. So this is really the interesting part. And you'll notice three distinct blips. And what is going on here is the electrons in the atom of a particular material. If you think of an electron in an atom attached to its nucleus by a spring, it wants to wiggle up and down at a particular frequency. And so those particular frequencies I'm going to show here. The closer you get to that frequency, the more the electron will wiggle, and that's what I'm graphing here, which corresponds to these blips in the index of refraction at those same points. So this is electron energy absorption. In other words, if I send a wave in here and it happens to be at the right frequency, the electron will actually absorb this energy and start wiggling up and down at that same frequency. If the incoming frequency is off from that, it won't absorb very much of the energy because it doesn't want to wiggle at that frequency. That's what this means. This absorption spectra of the electron is what causes the index of refraction to really change like this. Once you get near a absorption peak, the electron starts wiggling. If your frequency is slightly lower than the frequency the electron wants to wiggle at, there is going to be a lag or a delay between the wave coming in, the electron wiggling at that particular frequency, and then the electron then re-emitting the wave that you sent. The delay will increase as you approach its natural resonance. Once you get slightly above the frequency of natural resonance, the lag is reversed, which basically means the electron is more responsive to emitting at a slightly higher frequency than before. That need not make too much sense at this point, just more the fact that basically the lag that the electron gives to an incoming wave increases until it starts vibrating at its natural frequency, and then the lag drastically drops as the electron is finally able to respond at the frequency that it wants to. And then the lag continues to increase as you move further and further away from the desired resonance frequency of that electron. Because of that, you have many different regimes or different frequency ranges that are very, very different from each other. For instance, this right here is generally visible light for most materials. This would be ultraviolet. And all of this is really infrared, but the short infrared that we are interested in with, say, fiber optics ends here. And humans emit body heat at a mid-infrared somewhere around here. And the index here in this prism that I've shown you is in the visible. So as you can see, if you zoom in on this little particular piece, you'll get a graph of index versus frequency that generally looks like this. And so if people are only concerned with visible light, they'll say, oh, the index of refraction increases with frequency. And unfortunately, because people were so obsessed with only visible light, they called this dispersion normal. But then later on, of course, as they started to investigate other areas, such as parts of the infrared, or parts back here, where the index is actually slightly decreasing with frequency, they said, oh, that's weird, that's not like visible light in most materials, so we'll call that anomalous dispersion. But when you see this and hear this, just realize that that means in a particular frequency set that higher frequencies either have lower or higher index than other frequencies. In the visible spectrum, though, if you just want to remember that, because that's all you're really concerned with, just remember normal dispersion, and that index increases with frequency, almost always. But it's always important to remember where this came from, and that this form of delay, with the electron wiggling and absorbing energy before it re-emits the energy, is really what causes index of refraction in the first place. And because the electron wants to wiggle at certain frequencies, it's able to change the amount of delay it imparts to an incoming electromagnetic wave, like we have here. So that really is what dispersion is, and I'm going to end with a little example to give us some motivation on why dispersion is interesting. That hopefully is a little more interesting than, say, just another prism example. This is a Tolkowski diamond, which is pretty much the most common cut of diamond that everybody is used to. And the reason it is so common is because a Belgian engineer a long time ago named Tolkowski did a lot of optical analysis on diamond and basically determined that to get the maximum flashiness out of a diamond, this is the best cut that he could come up with, and I'm going to explain to you really quickly using dispersion how that works. So if we have some white light coming into the diamond here, now remember, it's important to note that the index of diamond is about 2.55, and this is air. So this comes straight in, and then because this index is so high, you actually have total internal reflection here. So because we have total internal reflection, we're just going to make the angle equal to itself as it bounces off. If I can draw this properly. And likewise, we're going to have it bounce off at, this should be a steeper angle, bounce off at the same angle. My apologies, my artwork is not so great today, but here we go. So now we have the white light total internally reflecting through the diamond before it comes to this interface. This angle here is not steep enough to be totally internally reflected, so I'm going to rotate this part where the light exits the diamond. So here's the diamond interface. We've got white light coming in like this. Because this is a visible light range, we can simply use the normal dispersion idea that index increases with frequency. So we'll start with red, which has the lowest index of refraction difference between the two. So for instance, we'll just say, for argument's sake, that the index of red is 2.53, which means the red will come out like this, and then the green, if it were 2.54, those numbers are slightly exaggerated just so that I can give angles that you can see. And then we have blue refracting even more because this index is even higher. So if we translate this over here, we have red, green, and blue. Now generally, this is the reason why we see so much color coming out of a diamond even if we shine white light on it, because it is showing the dispersion that is inherent in most materials. And because we're using visible light, you see the type of dispersion that is normal, where the blue is bending the most and red is bending the least. But Tolkowski, when he came up with this, really understood dispersion and analyzed it very carefully in order to come up with these precise angles in the cut of the diamond he came up with. This is just one good example of why understanding dispersion is so important. But if you were to truly do optical engineering and you were to use diamond for something, let's say that you wanted to, say, build an optical device for the military which worked in the mid-infrared range so that you could see body heat through buildings and see people through buildings. If you wanted to investigate diamond, you would need to understand that dispersion changes over a very large frequency range. So you would not be able to just say, oh, a Tolkowski diamond does this, therefore I will assume that my mid-infrared does the same thing. It's very important to have a very good understanding and a good feel for what dispersion truly is, so that you can take things beyond what have already been done today.